Hey guys, what's up? Spencer here. Today I'm going to be going over the theory and the applications of a recurrent neural network. Now, what type of data you could use with a recurrent neural network, you might ask? Well, it's largely related to sequential data, so time series or even text for that instance. So in this video, I'll be going over the theory and the applications of what you can utilize this model for. But before you even go into the realm of recurrent neural networks, I strongly recommend that you check out my other video on just the theory of artificial neural networks, and also maybe even an application of what you can even use with artificial neural networks, or like style GANs, different types of architectures, but in general it fits under the same umbrella. So do make sure you check those videos out, and also help out this video by liking this and maybe even subscribing. Check out my other videos and also my future content. Highly recommended, but let's get back to the video. So I basically just combined a bunch of the theory into a really neat slide deck on where there's a bunch of visualizations that are going to be occurring throughout the entire PowerPoint to illustrate what the overall architecture of the recurrent neural network is doing. So hopefully it makes it a little bit more clear just to conceptualize everything over here. So let me just highlight on the very first part of the drawbacks of the recurrent neural network. So one of the major drawbacks is the vanishing gradient idea, and this is essentially you trying, or your model trying to update its weights, but your weights are not being updated because your gradient is so close to zero. So your model is essentially not training on anything. And the other idea was the exploding gradient, where you are trying to update your weights, but your updates are so like massive that you're adding like a huge number to your weights, and your model just becomes like exponentially like explosive. So it's not really doing much in terms of just like capturing the details and then accurately predicting any reasonable results. But there are some other models that deal with this, like the LSTMs or the gurus. But we'll be doing that in a different video, a very future one. And yeah, but the other drawback of the recurrent neural network is that it can't retain long-term memory. So if it is training on, let's say, like you're trying to predict text, for instance, and it's training on like a 300-page book, and by the 200th page you're trying to predict the next page of output, for instance, it's not going to memorize or remember what it was training on, like on the very first page, for instance. Like maybe that's probably your most applicable part of your model. Maybe it has your glossary, I don't know, but it essentially cannot, like it can't retain a long-term memory advantage, where some other models might have that, like the LSTM or the gurus. And also, using the activation function, ReLU won't solve the issue of the vanishing gradient, which I mentioned earlier. And it just usually boils down to what type of optimizer or what type of activation function you could be utilizing. But using a ReLU is not the be-all, end-all. So over here, this is the input. This is just your input that you could be plugging into your model. And the very next part is that we have an initial state. So this initial state is essentially initialized with a vector just full of zeros, and this is a hyperparameter that can be tuned throughout however many epochs you're going to be using, and all of these zeros are going to ideally have different numbers, different weights associated with them. But each of these states over here, they always are going to be plugged into an activation function. So this initial state always has an activation function, and this will be a little bit more detailed and spelled out a little bit later in the slides. But over here, we have the input that's going to go to your next initial state, so your h_1, and your initial state over here, h_0, your hidden state, is going to be plugged into your hidden state as well. So let me step back a bit, and let's denote these as the weights. So I read this from X to A, where A stands for just the activation, and so this is going to be A to A. So we have the initial state, h_0. It always has an activation function, and we use the output of that activation function as an input to the next state as the input to the output. This will be a little bit more clear with a few equations, but we have these states, and we have the activation function, which I was saying earlier, of the very first state over here, where we are inputting our vector full of zeros into our output function, and it's usually very popular to use tanh or ReLU, but it really depends on what you are trying to do or what you're trying to optimize to within a specific range. But you are essentially going to utilize the activation outputs and the activation of your given, not your activation, your matrix multiplication of your input and your weights. So over here, you have the weights of activation to activation. You multiply your weights by your activation output from your initial state over here, and you add that to your weights of your orange line over here, and you matrix multiply that by your input, and then you add these two and you add some bias, and your bias is always going to be it's like your intercept term for your given hidden state, your very first hidden state over here. And then once you have all the outputs from input 1, input 2, you have one value over here, which is then going to be plugged into a different activation function over here. And that activation function would then just be multiplied by the blue weight of your hidden state 1, and you are going to have an output over here, y hat, with the superscript 1. So that is essentially the overall idea of the recurrent neural network. We can go take a step further. So once we have the output of our matrix multiplication for our initial state, for our input and our input for our initial state over here, we have the matrix multiplications, and you sum everything up, and then you get a new term. So the A1, these are the two exact same things, but they have different weights going to them. And then the cycle essentially just continues, where you are utilizing the A superscript 1 and the weights of A to A. You matrix multiply those two, and then you add the matrix multiplication of your next input with your different weight for your different value. You plug that into your activation function, then it outputs two other terms, which is going to be your activation output. And then you have your second activation value. You multiply that by your weights, and then you get one value over here. And then it keeps on going, and then it just does recursively. So hopefully that's a little bit more clear on what is going on in terms of visualizing the recurrent neural networks. And so note that the activation terms within this, the A's of 1 that are being outputted, so each hidden state can have a different activation function associated with that, but that's just a little bit more customization, and you can always play around with that. But that is essentially what the algorithm of the recurrent neural network is with visuals. So hopefully that's a little bit more clear, and if it doesn't really hit this spot, I'm going to be doing a coding demonstration on what that looks like. So there's going to be two parts to this overall algorithm that I'm going to be utilizing. I'm going to be doing multi-step forecasting, as well as just single state forecasting, as well as with all the architectures that's involved. But over here, there's going to be a Jupyter notebook. Everything's in Python for all Python lovers. And our very first step, we'll be loading in all of our packages. So of course, I have the standard data science packages where I have the math library and the data science library over here. This is the data scrape package that I'll be utilizing. And in previous video that I've done, it was essentially just doing financial data and how to scrape that stuff. I was using this a little bit more in detail. So make sure you check that video out if you are interested. I got a plotting package. I got some scaling over here, and then I'm using Keras, the most recent version, which is, I'm going to put that somewhere in the screen somewhere. I don't know off the top of my head. I would probably do like a pip list. But yeah, so I'm using these packages over here, and I'm doing a random seed, so you can definitely follow along on this. So let's let that load, and I'm going to be using the interval, just getting data from like just gold essentially, and we'll be predicting what the value of gold is, just utilizing the recurrent neural network. So this is where my interval is going to be. So I'm going to get about 5 years worth of data. Right now is December 20th. It's Sunday right now in 2020. So I'm getting pretty much like 5 years worth of data of gold over here. So let's load that in using our stock scraper over there. And this is the data that I will be using. Oh gosh, I really like using financial data because it's just it's like so clean and it's so easy to import and don't have to do all these headaches of just like further cleaning. But anyways, this is what we'll be using. We'll be predicting the adjusted close using the other values: high, low, open, close, and volume. So it's going to be a multivariate process. However, the very first step I'm going to be doing is a univariate time series, where I'm going to be calculating the percentage changes of our adjusted close, and we'd be predicting based on its own data. Just to keep it a little bit more simple, then we can be a little bit more complex there. So over here, let's plot this. This is the adjusted close. So if you invested in gold like 5 years ago, it's about $1,000. Is that what it was? Yeah, $1,000. You are a very rich person. It's like 100% rate of return. So that's really good over a 5-year time frame. That's excellent, actually. But over here, I'm just cleaning some data. I'm going to be using this data for in the future, just for the multivariate process, which is going to be a little bit different. And this is just doing some cleaning, and I'm scaling everything. But over here, this is the data I'll be using for the univariate example over here. So this is what I'll be utilizing: returns. So this is the percentage change. Note that our very first observation is going to be an NA, because we're always going to do like this approach of where we have to calculate the percentage change, and the very first observation is just nulled out because there's no change happening. Just using that as a point. But yeah, these are all percentages, so this can be read as 0.65%, 0.5, etc. So let's plot what that looks like. And this is what my returns looks like. So it looks like the max that I've lost in like a given day, from day to day on adjusted close, was like 4%, and the max gain was like 6%. So it's pretty cool. Let's look at the histogram real quick over here. So it actually looks pretty normal, sort of. But that's a really cool graph. You can always take a look at that, and it's like a really nice bell curve almost. That's really cool. But over here, this is where we're going to do a little bit more of cleaning. So I'm essentially going to be reshaping my entire data set into basically an n/1 matrix. So just basically mash everything together. And this is what that function does over here. So I'm just going to call this like a NumPy array. So I get the returns, I call the values, which is just the observations minus all of the row names and the column names. It doesn't like that, so it ignores that. It just gets those values, index it at the very first one, so I ignore the NA values and I reshape it. So the -1 on the reshape just means that it's a Python interpreter on where it is essentially just given a one dimension over here, it will automatically recalculate however many dimensions it needs to be over here based on the original dimensions of our shape. So since our data were already an n/1 matrix over here, the rows is just going to be the same amount of the rows that I have up here, which was like 1331. So, and then I just mash that down to that very first column. And I'll print that out for the NPA NumPy array. And then last but not least, I will scale it. This is by default, but I decided just to write it out for more clarity. Now I'm going to be going between a range of 0 and 1 for the scale, and then just call scale.fitTransform on the NumPy array. And we can print out the length over here. So we have 1330 values. So that makes sense, right? Initially we had 1331, but that's because we took out the very first value over here, and now we have 1330. So that is the length. And the next step is to essentially just calculate the time series data. So essentially, since everything has to be sequential in terms of training the model, and it leads to one specific output. So you're given 10x values, and you try to predict that one output over here. So using a little bit more of a visual, let's say I'm trying to predict 3 days or 1 day in advance using the past 2 days. So I'll be using 1, 2, these first two values, and I'm trying to predict this value. That's essentially what time series is. You're using the values right before the predicted value, right? But you're given that very block right there, and you're trying to predict that given output. So using first two values, predict what that is. And then next, using these two values, predict what that is. And so since we're training, these are all true values, but it'll be a little bit more complicated when it comes to actually predicting like out of sample data. And so yeah, over here. So a little bit more in detail. So I'll be using 10 historical data points to predict one step ahead. And I don't really use this variable because I'm already indexing over here and it already accounts for that. But over here we have the X, and we are essentially just creating our train X and our train Y values. So I'm just appending the NumPy arrays. So I index at 0 over here. So 0 to the I plus samples. So it's going to be 0, 10 values. So we gain the very first 10 values, 0 to 9. Yeah, 0 to 9 values. And then we're going to be getting the 10th value. So it'll be at 10. Remember that Python stays at 0. So the next step over is going to be retaining that value. And I'll be using that as a Y. So this is predicting one day ahead using the past 10 values. That's essentially what it's doing. And I just for loop it, and I just append it to the X and Y over here. So let's run this, and this is just a snippet of what it will look like. I just essentially just printed out what that length is going to be. Got 10 over here, and then one value of predictions that are going to be over here. So these are going to be 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is going to be the 11th value where we are predicting on itself. So hopefully that makes sense. It's basically like a train, and then you have a head. You use the body to predict the head, and then it keeps on going. So over here we have some reshaping over here. Notice that I have 1320 observations instead of 1330. This is because of the minus samples over here, since we wanted to incorporate the one step ahead prediction. So that's what was being done here. So we are expecting 1320. I'll also be using a threshold of 90% of our data will be considered to be training data, and the latter 10% of the data will be used as a testing data. And so the threshold is 1188, so I'll just be calling the very first 1188 values, and then the 1330 minus the 1188 values for the testing part. So that's being done here. So next step is to create your architecture, and this is probably where it gets really interesting in terms of trying to maximize your model complexity to get your best results and all that stuff. So it takes a lot of thinking on what type of layers you would want, and also how many units, what type of activation functions you want to use, so on and so forth. And this is where like all the expensive cost analysis and nifty math comes into play. But over here I'm starting really simple. I'm using the Keras library, the sequential over here, just to line up everything, and it's so easy to use. So first part, I'm adding one layer with 3 hidden units. So remember in our in the PowerPoint, one of those hidden states pointing to the next hidden state, and then you have your input that's putting in. We have like 3 units of those. So yeah, so that is our hidden layer. And then just for our next part over here is a dropout layer. This helps with the overfitting idea, where it will take out a good chunk of our, well, in this case 20% of our training data, and essentially just like ignore it. And this helps prevent the overall overfitting idea, where you have underfitting or overfitting. So hopefully our model does not memorize the past data, because we don't want that. We just want it to recognize patterns and act on those patterns. And then last part, I just added a dense layer of 1 unit, and this is essentially because we are predicting essentially like this is like a regression problem, so we only need 1 hidden unit. Well, we only need one unit in our output layer, so that's why we're using that. And then one of the more important pieces over here, I'm using the loss function of mean squared error, and I'm using the Adam optimizer over here. So we don't really necessarily have to worry about learning rate, because the intricacies of the Adam optimizer is pretty good. I think it's like default 0.01, so we don't really need to hypertune that. And then I'm just printing out the architecture. So this is what it looks like. We got a sequential model going on. We got the RNN with 3 hidden layers, or 3 units. We got a dropout layer, and we have a dense layer. 19 parameters. So pretty simple. And then we'll be training on this. So this is the threshold. I'm be getting the first 1188 values, which is our threshold value, and then the first 1188 values over here. I don't need to shuffle. In fact, we don't want to shuffle. I just included a few parameters that I deemed very important into the overall scope. But shuffling is essentially just like randomizing your observations and just plugging in for you. So you don't really have to worry about randomizing your data when you're plugging into your model.fit. So it's a really neat function. I'm using 100 epochs and batch size 32 and validation split 20%. So I go a little bit more in detail on what the values of this essentially is like representing. And I did a previous video on a artificial neural network, and I go into detail a little bit more on how these work. But high level, this is just a for loop that's just iterating through. This is however many observations you want to plug into, and this is however many of those batch sizes to of your training data to actually compare the results to, and then judge how well it's doing in the middle of its training session. Verbose equals 1. This is just outputting, just spitting out data, which is this. This is verbose 1. If you equal it to 0, then you're not going to get any output, and it'll be running behind the scenes. So we have over here, we got the training loss, we have the validation loss. Ran really fast, which is to be expected because it's pretty simple. And over here, this is what our training loss and validation loss looks like. So rule of thumb, this is really cool to just know. I even put in a few notes over here. If your training loss is much greater than your validation loss, then you're going to be underfitting, and vice versa. So if your training loss is much lower than your validation loss, then you are overfitting. So in this case, our validation loss is over here. So it's a little bit greater than our training loss. And so that just means we are overfitting. And that means that our data is essentially memorizing the training data, and it's just using the training data to output your test data. So it's not really getting, it's not really understanding the patterns, which is, you have to play around with it to get a really neat, robust model. And it usually comes down to what type of data you are using. And in our case, there's so many other factors that are involved in order to predict the next price of gold. Usually politics, but we don't have to go in there. That'd be a future topic, a very large topic. So over here, I am going to be utilizing what many other folks have not really been doing in terms of just guides and all that. And this is a multi-step forecast. So what happens if we want to predict, a few days in advance instead of just doing a one step ahead? And many people have been doing it wrong, but this is what you should be doing if you want to predict a little bit more out of scope. Well, using your overall data set, and then just continue to step into the future to get a more robust prediction. So starting over here, we have our true Y values. So at the 1188th index, we get the rest of the data, and this is just gonna be our true values, which is fine. We're gonna have an array with the just empty array, and we're gonna be putting in our values over here. So this is the number of forecasts that we're gonna be doing is gonna be 132, and our latest input. So this is going to be our most recent X variable inside of our testing realm. So it's going to be our latest input. So this is going to be our 1188th value, and we'll be plugging that in to our prediction so we can get one step ahead. But this is where the tricky part comes into play. We're going to be appending our prediction to our pred y over here, but we are then going to update our latest input with that given prediction over here. So it's going to be somewhat of a rolling window, or a sliding window, as you might call it, where we are essentially going to be chopping off our oldest observation and appending our newest observation. So it will keep on rolling, so to say. So if you have a computer science background, you can think of it as a circular array. But it's essentially just like stepping through. So like you're always it's like a conveyor belt. It's always going to be moving along, and your older values are going to be chopped out, and your newer values are going to be plugged in. So it's going to be like a LIFO if you're in the operation systems or industrial ISE, industrial systems engineer. So last in, first out. Yeah, so it's going to be like doing something like that. So that is essentially what that is doing over here. And high level overview, it's essentially just going to be using the predictions that you are using to predict your other predictions. That's essentially how you do the multi-step forecast for a time series. So let's run that. It's running real quick. So it's going to be doing 132 of these values, and this is what our values will look like. So notice our forecasted values pretty much are like a flat line, which is pretty much to be expected. It's just using the previous value as the given prediction. It will keep on doing that, and that just says that your model is essentially like not good enough, and it's not really getting the trends over there. So yeah, I'll be using this value over here, PCT_C_gold, and that is essentially this. So we're gonna be using 1, 2, 3, 4, 5. We're gonna be using 5 of these columns over here that we got over here, and we're gonna be predicting the adjusted close over here. And notice that everything is normalized between 0 and 1 using that min scalar. And I did that a little bit previously, all the way up above. I just went over it really quick just to go to the univariate time series forecasting. But we're gonna be doing essentially the exact same thing. We are going to essentially create our time series data set that we'll be training on. We have our X and our Y. We are going to be appending these values, and the only thing that's different is that our columns, number of columns that we are using, is, since it's multivariate, we are using multiple variables inside of our prediction output. So we can have 5 columns, which is 1, 2, 3, 4, 5, high to volume as our X variables, and our fifth column, well, our last column is going to be the adjusted column. So 0, 1, 2, 3, 4, 5, we're going to be calling here. Note that 0 to 5, it does not include that most recent value. Same thing over here. So yeah, that is essentially what's happening here. We're going to be running that, and this is what our data looks like here. So we have 1, 2, 3, 4, 5 values for our first observation. So the first 5 values represent, that very first row of our independent values, which is fine. And then over here, this is what our dimensions look like. We just convert everything to an array. We have 1321 values now, 1321, and then we have 10 observations per array, but it has 5 columns inside of each of these arrays you got going over here. And of course, we only have like one output, like a scalar value for our y's, because we're only trying to predict a y value. So over here, do some additional cleaning. We get the threshold again at 9% of our x dot shape over here, and that will essentially just act as a splitter for our train x shape, which is this, our train y shape, test x and test y. So this is what we are working with. And I went ahead and I just ran the recurrent neural network, but it's essentially the same architecture. I'm just making it a little bit more complex since we have additional complexity for our input. So I have 30 internal units, and using the same activation function tanh, using the same bias, and of course we have the same input shape, where the input shapes refer to number of rows and the number of features, which is in this case like number of columns, which is 5, so it'll be 10 and 5. And have the dropout rate over here, incorporate the dense layer for the regression, and model summary, and this is what our output looks like over here. So let's fit that data real quick. It will take a little bit longer, but notice that it's very similar to that of a univariate time series. The overall structure and the overall architecture in terms of just like plugging in additional data for other future predictions. That's essentially what it all really is, and it looks like it's done. So let's do the training loss. That looks that looks all right. I mean, it's not that much different from each other, but time series is a little bit wonky. And this is the one time step ahead forecast. So it initially looks pretty good, but you have to remind yourself, like, the if this was that good, in the overall financial realm, then someone will not be so very much inclined to provide their model like this, like the RNNs, because they'll be like a billionaire or millionaire. But if you were to utilize this, if you look at it a little bit closer, right, you're essentially using the very first, well, basically your historical data to predict your next increment of your data. So, and also look at how off it is usually. So that can mean the difference between a loss of 50% or an increase of 50%. And there's definitely a lot more research that needs to be done, but then again, I'm not a financial expert, so do take it as you will. But this is essentially a one-step time forecast. And also, if you want to do your multi-step forecast, which I've done earlier for the single univariate time series, you would have to come up with a very clever idea to come up with predictions for the independent variables as well to get your new prediction. So you'll essentially be predicting 6 columns, since our data that we are working with, what was it, 5? It was 1, 2, 3, 4, 5. Yeah, you will be predicting like all 5 of these values when you are multi-stepping through, because you would have to have your new values for your high, low, open, close volume, and you try to predict your adjusted close, which you are going to be appending to your input values. So that can be definitely a little bit tricky, but it's the same idea on how you would do a multi-step forecast. There's just additional models that you might have to do in order to predict one space. You could probably run linear, parallel, recurrent neural networks for just predicting each individual piece. That'll be sort of interesting. But yeah, that's essentially all you really need to know for a simple recurrent neural network. You have the theory and you have the applications on. You can use this model for whatever you might use. So have at it.